Hello, my name's Colin Sauze. I'm a research software engineer at Aberystwyth University in mid Wales. I was going to talk about trying to build sort of miniature supercomputers or high-performance computers with the Raspberry Pi, my experiences of doing it. I'm just intrigued, does anyone actually here have any familiarity with high-performance computing or building even Raspberry Pi clusters? No? Okay, so this is all new to everyone. So I'm going to talk a bit about me and how I kind of got to doing this. I'll give you a brief overview of what I mean by high-performance computing, as it seems most of you don't know. Why I'm using a Raspberry Pi to teach it instead of using a real supercomputer. What I've built myself, and then a bit about my experiences of doing it. So I work in a project called Supercomputing Wales, who provides high-performance computing facilities for 4 of the big Welsh universities. So ourselves, Aberystwyth in the middle, Bangor University in the north, and Swansea and Cardiff in the south. And between us, we've actually got 2 physical large supercomputers. One is in Swansea and one is in Cardiff, but we all share them equally. Now, I actually came into this from a rather odd background. My PhD was a few years ago in robotics, and I'm also here with the AberSailBot team, who are outside with their sailing robots. So you may wonder how someone who did robotics ended up working on supercomputers. Well, the thing is, I actually did this first. I did an undergraduate placement while I was doing my degree, and I spent a year working in Hewlett-Packard dealing with supercomputers. And it's kind of something that keeps coming back to haunt me of there are more opportunities to do that than there are to do robotics, unfortunately. But I do like to try and find ways I can play with things like Raspberry Pis, and this is my attempt to combine that with my day job. So what is a high-performance computer, or a supercomputer as you might call it? Normally they are lots and lots of relatively ordinary but pretty high-end computers that are all linked together to form one much larger computer, and you can distribute work across all of these. So usually they're high-end servers that each one will have tens of CPU cores, hundreds of gigabytes of memory, and a very high-speed network that links them all together. And then there'll just be 1 or 2 that users actually log into, and that's where they submit jobs that go off and run on all of the others. So they'll distribute the job across all the other ones, it will go off and do some calculations and come back with an answer. And I will say this feels like going back 50 or 60 years in computing to the days of punch cards, where you rotate your program on a machine that produced the punch card, you gave the punch card to the computer operator, they would put it in a queue and wait for some time, free on the computer. They'd run your program, and they'd give you back a printout of your results at the end, probably with an error on line 2. And it kind of still feels like that a bit with supercomputers. We also have massive disks, because people these days work on very large data sets. So we normally have hundreds, if not thousands, of terabytes of hard disk attached to these things. But at the end of the day, they are basically normal Linux computers. They run typically Red Hat Enterprise Linux or CentOS if people don't want to spend money on Red Hat. And they look and feel like any other Linux computer when you use them. They have a command prompt and you SSH into them, and they run all the same programs that you can normally run. So what's this actually used for? It's used for sort of lots of big scientific problems that involve vast numbers of calculations. So traditionally this was things like simulating physics simulations. So we've got a group who look at the sun, and they are trying to study things like sunspots and coronal mass ejections, where the sun fires out loads of charged particles, and they're trying to simulate what's going on inside the sun. And they're trying to analyze thousands and thousands of images of the sun. It's also used in a lot of engineering things to work out stresses and strains in materials, to work out airflow around things, to design cars and planes and wind turbines to be more aerodynamic. Weather forecasting makes huge use of this. We've just had the news last week. The Met Office have just been told they're going to spend £1 billion over 10 years on their next generation supercomputer to try and improve the accuracy and the resolution of their weather forecasts. A lot of people doing earthquake studies do it to model how the Earth moves. People doing flood studies as well, the same thing. And then there's sort of more recently what we call the big data type problems. And this is where instead of trying to simulate something and do huge amounts of maths, you've also got a very large data set that you're trying to process. So a lot of the work I do on a day-to-day basis is working with people doing gene sequencing and trying to match, is this gene sequence I found from something that we already know about? Is this thing a particular bacteria? Do we know what it is? And that involves trying to match one pattern against libraries of billions of others. I also do a lot of work with people doing satellite imaging, and that's what this picture here is showing. So this is a map of all of the mangrove forests in the world, and they've been looking at satellite pictures from every few days for 20 or 30 years trying to work out where the mangrove forests are growing and where they're disappearing. And also the big one recently is training up artificial intelligence neural networks to do image recognition. And this picture here is it trying to detect some breast cancer from some medical images. So I don't know how well you can see it, but there is little red circles around that where the computer thinks there is cancer in the image. So where does the Raspberry Pi fit into this? Well, we've seen for years, actually, that I found all these different articles of people trying to build little mini clusters out of Raspberry Pis. And there's been lots of different designs. You can now go out and buy from Pi Moroni this version with 4 Raspberry Pi Zeros and then 1 Raspberry Pi 3, I think that is, underneath. And then you can kind of do the same thing across those. Now, it's not going to be fast, but if you want to learn what you're doing, then that works quite nicely. And some people have taken to building fairly big ones, and there's actually one out there in America that's got 750 Raspberry Pis in it, in one sort of 4U case, which is probably about the size of this table and about that high. So just compare what a Raspberry Pi looks like compared to a normal supercomputer. We've got 1 core on something like the Raspberry Pi Zero, up to about 4 cores on the best on the Raspberry Pi 3 and 4. In a real supercomputer, we'd have between 20 and 64 cores in each of our nodes, our individual computers. In the Raspberry Pi, we've got between 256 and some of the oldest ones and 4 gigabytes of memory on each. So that works out at between 256 and 1 gigabyte of memory for each core, because each of those cores might be doing something simultaneously. But on the real supercomputer, there's hundreds, maybe even thousands of gigabytes of memory, and this can translate to anything from 2 to typically 64 gigabytes of memory per core. On the Raspberry Pi, we've got a pretty slow network interface with our Ethernet. It's either 100 megabit or, on the latest ones, gigabit Ethernet. But in reality, the way it's wired up to the USB on those, it doesn't get those kind of speeds. So you're lucky if you get 100 megabits, maybe a few hundred on the Raspberry Pi 4. And the latency, that's the time it takes the message to get from your computer to the other computer, is normally measured in tens or hundreds of microseconds. When you compare that to messages sent around inside a computer, you're talking about nanoseconds. So you're talking about thousands of times longer for a message to get sent from one Raspberry Pi to another than it would internally to get from one core in the Raspberry Pi to another core. And that obviously has a big effect on how you can write applications. So on real supercomputers, we have a thing we call an interconnect, and the most common one of those is by a company called InfiniBand. And theirs go at 25 or 50 gigabits a second, and there's still a few microseconds of latency. You've got storage. Obviously, in the Raspberry Pi, we've got SD cards, and I think they go up to a few hundred gigabytes now. I think there may be a terabyte one available, but they're not cheap. Or we can plug in a USB hard disk, but not the fastest thing in the world because it's going over USB. On a real supercomputer, we will have hundreds of disks in giant arrays, and they'll form thousands of terabytes of space quite often. And then software. Normally on our Raspberry Pis, most of us are probably running Raspbian Linux of some form. There are other Linux distributions available. On supercomputers, we're typically still using Red Hat and CentOS. Some use Debian, which is the same as what we've got in the Pi, but it's not that common yet. So why do I want to build a Raspberry Pi cluster? I mean, clearly it's much, much slower than a real supercomputer. And it's too slow to do any real work. And I've seen a few times people have posted on the internet going, I built this thing, I can now compute something amazing. Well, actually, your desktop computer would do it faster. So from that point of view, there is no point. But they're great for teaching people, because whenever I've taught people how to use a real supercomputer, one of the things I find is that they're a bit scared of it. They're being let loose on this multi-million-pound piece of equipment for the first time, and a lot of them don't really know what they're doing, and they're worried they're going to break it, which isn't a bad thing to be worried about. But if I let them play with a Raspberry Pi cluster that costs 100 or 200 pounds, they feel a lot more relaxed about doing that. And these real systems are busy. People are doing real research on them, and sometimes when we want to run things in a class, we have to wait for other people to finish their work before we can actually go and launch it. If we bring our own little system with us, we can do what we like on it. And we've got a lot more control over the whole environment, and it's there in front of them. These real computers, they're out in a basement in some building somewhere that no ordinary person is going to go and see. Even in Aberystwyth, we don't have our own system on site. It's in Swansea University. That's 2 hours' drive away. And even the people in Swansea, they're never going to go and see the machine. It's hidden in the building they don't work in. And finally, a lot of people don't end up getting accounts sorted out because it takes a few days and we have to go through an approval process to get people online. And when someone's signed up for a course 2 hours before it's actually being delivered, they don't have an account sorted out. So to have a system that I completely control and go, yes, there's an account done, versus something they have to apply for and wait for someone else to click approve on and go through some bureaucracy as to whether they're allowed to use it or not, it's much easier just to have something there that I can make them use. So this is a picture of my little Raspberry Pi cluster. I called it Tweety Pi because all the other computers in supercomputing Wales are named after birds. And it's made entirely of things I begged, borrowed, and stole from around the university. I didn't actually buy anything to build this. So I have 10 of the original Raspberry Pi Model 1s, the ones that came out in 2013. Was it 2012? 2012, I think. And they only have a single processor core. They are pretty slow. They have 512 meg of memory. They only have 2 USB ports and Ethernet, no Wi-Fi. And that's what you can see in these stacks of boxes here. And then I found that using one of those as the login node that does all the running of it was a bit too slow, so I replaced that with the Raspberry Pi 3, which I think is just there under the monitor, and that's what's displaying on screen. And they're all running normal Raspbian, and the one that's at the head of it, the Raspberry Pi 3, is also a Wi-Fi access point, so anyone can open up their laptop and connect to it and then log in and run a job. You don't need a screen and a keyboard plugged in to actually do anything. One thing this does all need is it needs to have internet access. And the reason it needs to have internet access is you've got to have a common time signal across all of them. And they all need to have the same idea of what the time is. And the best way of getting the time, because the Raspberry Pi doesn't have a clock module, is to actually plug them into the internet, and then they get their time via a thing called Network Time Protocol off the internet. So just in the background there is a white little old netbook, and that is there just to provide internet to get the time signal. So I kind of ran out of time when I was building this last year to write any really nice demo software. So I wrote this very simple thing that calculates the value of pi using something called a Monte Carlo method. So these are called Monte Carlo because they're running lots and lots of random numbers through to create a simulation. And the way this one works is you draw a square, and then you draw a quarter of a circle in that square, and you drop points randomly in it. And the number of points that appear inside the circle versus the number that appear outside the circle, the ratio between those gives you an approximation of pi. And the more points you drop, the better your result is. But the more points you drop, the longer it takes to compute it. So I have a little program where you've got some sliders, and you can choose how many computers you want to do the calculation, how many points you want to calculate, and then you submit go, and it will go off and run it on the cluster. And it will break that job up across however many nodes you ask to run it. So if you ask for 10 of them and you want 10,000 points, each one will go and compute 1,000 points. And then they'll all come back to the master one, which will compute the answer at the end. And that's a very good model for how all distributed computing works on these real big supercomputers. And that's exactly the same sort of method you might use if you were doing some kind of physics or chemistry simulation. My colleagues at Swansea University, they do a lot of airflow modelling, and they actually did the modelling for the Bloodhound supersonic car that's currently in South Africa trying to break the world land speed record. And they wrote a cut-down version of that software for their own Raspberry Pi cluster, and this uses a Kinect, a 3D camera, to kind of draw a picture of you, and then work out how, if there was air blowing around you, how it would flow. So this is imagining the air coming from the left to the right, and that shows how the air would move around, and that's me holding my son, around us if we were kind of floating in air. That needs a bit more computing power than what I had. They've got 16 Raspberry Pi 3s, so that's 4 times 16 cores, so what's that, 64 cores. I've got 10 Raspberry Pi 1s, which are slower anyway, and only have 10 cores. Theirs takes about 3 minutes to run each job. I think that would take too long for me to run it. But maybe one day I'll find some faster Raspberry Pis. I also found that the group in Edinburgh who run the UK's national supercomputer have written a load of demos for their own little Raspberry Pi cluster, and they're all on this website here under EPCC-ED, but I haven't had a chance to try any of them out yet. So one of the other things I want to do was make this as realistic as possible compared to the real environment of a real supercomputer, because I'm using this to train up people who might use a real one day. And I installed basically all the same software that I have on the real system. So I installed MPI, which is the Message Passing Interface Library. that is used for programs to coordinate with each other. I installed a program called Slurm, which is the job manager that lets you run jobs across all of those. I put quotas on their home directories, so they can only save a certain amount of data. And then all the home directories are shared across a network mount, so the file you create on one node is there on all of them. On real supercomputers, we have a big problem where we often need different versions of the same program. So different people will need different versions. So we have a thing called loadable modules, where you can choose to load in extra bits of software. So instead of installing them normally as a system package, you install them in these special modules. And I went and set that up as well. And finally, I wanted them all to boot off the network, because I didn't want to have to be duplicating SD cards every time I changed something, or running the same command 10 times over to install the same package on every single Raspberry Pi. Unfortunately, there's a slight problem with that. The older Raspberry Pis that I'm using don't support network booting. So the newer ones can do this, but the older ones don't. But I found a slight workaround, is I put the kernel and the bootloader, which is the small 50, 100 megabyte partition you get on the SD card. I put those on the SD card, but then didn't put anything else. So there's enough there to load the first steps of the booting. And what they then do is mount their root file system, which is normally the bigger partition that you have on the SD card, over the network, and then they run that off the network. So then they're all running off the same copy of the file system on the network. And if anyone's interested, that's the line I changed in command line txt to do that. And this means that although I have an SD card in each of them, there's a very small amount of stuff on it, and they're all identical. So if one of them breaks, I can have a spare one, or I can very quickly reload what's on there. I always find that whenever SD cards break and you've got to reload the whole operating system, you're normally there for half an hour at least. And I find that really frustrating, because they always seem to break whenever I need them most. Whereas with this, it takes about 2 minutes to reload the SD card. So I also made some teaching materials, and this is what I teach people with. So very quickly, I teach them what a high-performance computer is. I show them how to log in, show them how to copy some data to and from it, show them how to monitor their jobs, a bit about profiling, which means measuring which bits of your code are causing the problems and taking the time, and then how to run your code in parallel across all of these computers. And I've now run this course twice, and my experience has been that I've had this with a group of new PhD students and then a group, a mixture of staff and PhDs. Most of these people have some Linux experience, but nothing with high-performance computing. They like seeing the real hardware because they're never going to see the real thing, and it just makes it a bit more tangible as to what you're actually playing with. It was really good to work around the delays in creating accounts. I did one where we simultaneously taught on the Raspberry Pi and the real system, and people could choose which one they did, and that worked really nicely, and people were seamlessly going from one to the other, so obviously I duplicated the environment well enough. And it makes it much, much more obvious what your limits are, that often people who don't really know what they're doing make silly mistakes, but they're not immediately obvious on these fast computers because they've got so much memory and so much disk and so much computing that they don't realize. But when you've got a small Raspberry Pi, it becomes immediately obvious that you've done something stupid and you're eating all the memory. And all that makes people a bit more adventurous in what they try, and I think that really helps the learning environment. So just a quick bit of future work I intend is to try and automate the configuration a bit more. So right now I have a script that deploys the SD card, but we have lots of professional tools out there for doing this, things like Ansible and Chef and Puppet and Salt. So I'd like to try and use them. I would like to try and switch to using CentOS, which is much more like the Red Hat Enterprise Linux that you can get. It is available for the Raspberry Pi, but it's not as well supported as Raspbian. And right now I do have to create user accounts on every Pi manually, and I want to try and automate that. And finally, I want to try and get a better demo, and one I'd really like to do is we have a project called Monster Lab. And in Monster Lab, you make a monster by joining Lego bricks together, and each Lego brick is one gene of the monster, and the color tells you about it. So one of them will be the number of heads it's got, one will be the number of eyes, one will tell you how many arms it's got, one will tell you how many legs. And you feed it through this machine here, which basically finds out the color, and it tells you all the attributes of your monster, and then the kids at the moment go and draw it. Well, I'd like to try and simulate that with a physics simulation, and then run that on the cluster so they can see that. Or try and do a gene sequence match and see what other monsters were similar to that monster. So finally, if you want to see more about this, all of the setup instructions and scripts that I've made are on my GitHub page, and there's all of my teaching material there or my email address. I don't know if we've got a couple of minutes for questions. Yeah.
Other than the teaching, are there any good uses of clusters of Raspberry Pis?
The only other one I've seen is to do sort of load balance type website stuff. So the Raspberry Pi Foundation a while ago actually ran some of their website off their Raspberry Pis. So when you went to raspberrypi.org, I think about 1 in 10 requests went through to a real Raspberry Pi. The other place they might really have an edge is on the power consumption versus the amount of processing power. So there's been a big push recently, and using ARM chips on bigger systems as well, that the amount of power you use for the amount of computing you get may be better than a desktop computer. And certainly if you wanted to do something, say, solar-powered or battery-powered, then that might make a lot of sense. But in terms of raw compute power, they're never going to be able to compete. Okay. Nobody else?